Okay, so I guess we're going to go ahead and get started. Welcome everyone to the shared mobility track of BTR. My name is Atiyya. I'll be moderating today's session. So just as a quick reminder to our presenters, we have 15 minutes for the presentations, followed by 5 minutes for Q&A. And if the audience members could just keep the Q&A questions in the chat box, I'll try to consolidate and ask during our time slots. And as you can see, we have a range of shared mobility presentations, from shared AVs to on-demand shared mobility services, shared ride hailing. So I'm really excited for today's session. And our first presenter can go ahead and start sharing her screen and getting into presentation mode while I introduce her. Okay, so Kristine Miller is a senior associate at the Goodman Corporation. At TGC, Kristy leads and supports the development, planning, and implementation of various community, regional planning, transportation, and infrastructure projects. Prior to joining TGC, Kristy spent over a decade focused on public transportation-related research at both the Singapore University of Technology and Design and Texas A&M. Kristy holds a Master of Urban Planning degree from Texas A&M University and is a certified planner with the American Planning Association. And Kristy will be presenting on understanding the acceptance of shared autonomous vehicles among people with different mobility and communication needs. So with that, please go ahead and get started, Kristy.
Great, thank you. Hi, everyone. Thanks for joining us today. Like she said, I'm Kristy, and on behalf of the research team at SUTD, I'll be presenting our recently published research. So we'll just get right into it. So here's a quick outline of our presentation today. I'll briefly provide research and context and review the research objective. We'll discuss the study groups and the methods used, and then summarize the survey findings and outcomes of the focus group discussions. And then we'll discuss some recommendations and implications for AVs and public transportation. So just for site context, our research was focused on public transportation in the Southeast Asian city-state of Singapore. Singapore is 719 square kilometers or 281 square miles with a population of approximately 5.7 million people. Pre-pandemic, there were an average of 6.7 million trips taken on public transportation per day across the nation's 350 bus routes, 200 kilometers of subway, and 28 kilometers of light rail. Singapore was ranked the top nation in KPMG's 2020 AV Readiness Index for its readiness and capability to adopt AVs, and has been testing AVs on public roads since 2018. Singapore authorities have also announced that AVs will be deployed in public transportation in 3 newly developed areas by the mid-2020s. So the primary objective of our study was to understand the emotions, attitude, confidence, perceived benefits and concerns, and service expectations among people with different mobility and communication needs once AVs are introduced into public transportation. In order to fulfill this research objective, we identified the 6 groups listed here who may be more impacted when using public transportation without a driver and may need some special accommodations. We utilized a mixed methods survey and follow-up focus groups to go more in depth on some of the survey results, which we'll talk about later. All of our participants were Singapore citizens or permanent residents over 18 with basic proficiency in English and have no conflicts of interest with any of our project partners, and then also identify with one or more of these target population segments. Recruitment for the survey was through an open call for participants, outreach from the relevant community agencies in Singapore, and then social media advertising and snowball sampling. The survey was open from September 5th, 2020 through January 15th, 2021, and a total of 300 individuals from our 6 groups completed the survey, so 50 per group. To accommodate the different preferences and circumstances, anyone eligible to take the survey had the option to complete the survey online or over the phone or over Zoom or in person. In the online survey, participants self-selected their own answers, but over the phone, video, or in person, the interviewer asked questions and then entered the response as dictated by the participant. Those who completed the survey received 30 Singapore dollars in grocery vouchers as an incentive. And then to further understand whether our target population segments differed from the general population, and if so, how, In the paper, we made some additional comparisons of the findings against a sample from the general population who took a similar survey at the same time as well. Questions in our survey can be grouped into these following categories: understanding of AVs, your feelings and emotions and attitudes toward AVs, your perception and then expectations of AVs, and then how you might accept them or how willing are you to try something, and then how the introduction of AVs in public transportation could impact your travel needs. So to gauge the perception of AVs in separate questions, participants were shown service-related attributes, potential benefits, and potential concerns that could arise from the implementation of AVs in public transportation. So they responded to each one on each concern on a 5-point Likert scale, ranging from 1 where they strongly disagree to 5 where they would strongly agree. And then there was also a do not know option available too. So this summarizes all of those results and shows you the top 3 for each group. So the first section in blue shows the service expectations. Consistent across the target populations, the top expected service attribute was that the AV in service would be safe and be reliable. Groups that were likely to require onboard assistance prioritized ease of boarding and alighting. So people who might need the driver to open the ramp for them or help them onto the bus. The middle section in yellow shows the perceived benefits of AVs, which were largely similar across all the groups. It was consistent that the top 2 perceived benefits were that AVs in public transport would reduce vehicle emissions and also lower manpower needs. And then on the bottom in yellow shows the perceived concerns of AVs, which varied widely across the groups, but the top 2 were that the AV's ability to react in unexpected situations, and then also potential technical fault in AVs. So finally, participants from the target groups completed a qualitative section in the survey that had open-ended questions investigating how the introduction of AVs in public transportation without a bus driver or staff on board may impact these travel needs. We used thematic analysis to analyze the responses, and patterns within the responses were used to create and refine categories as new insights emerged throughout the initial and final coding processes. Shown on the screen are the main themes for each group, and there were several overarching themes emerged from this analysis of responses. So providing trial and familiarization experiential rides on AVs was the most frequent suggestion expressed across the groups as participants sought firsthand experience and interaction with the new technology. Current challenges using public buses could be exacerbated when there's no driver present. So trial rides will help assure these groups of their ability to adapt to using AVs without having their needs compromised. So such as learning the interior configuration for blind and visually impaired, we heard that from them. And then also participants using mobility aids, they need to make sure that there's room or enough room and how to board the bus and the best way to secure themselves. And then also how to hail the AV and where to wait for it at the bus stop. And then where the location of the doors, and are they going to be at the same spot every time the bus lands at the bus stop? So as there are no operators on board, participants want assurance that they'll be able to access assistance if needed. They suggested including clearly indicated means of seeking assistance when they need it, and they're expecting to be able to communicate with a remote operator at a control center on demand when or if necessary. And they were kind of flexible on how they wanted to see this. It could be in the form of an intercom or just an emergency stop button or just a way to get out, and assuming those things would be placed at an accessible height so you could reach them. And in Singapore, bus drivers manually deploy the ramp on the public transportation vehicles and assist the passengers if they need to use the ramp. So some groups indicated that they would like to have onboard staff or passengers be able to assist, particularly while they're boarding or alighting, or if they need to use the ramp. And they would also, our participants would also like to be assured of their safety around and outside of the AV while they're boarding and alighting, and then also when they're traveling on the AV without any operator on board. They shared a desire to be assured that there would be constant monitoring of the AV's operation in the interior of the vehicle for onboard security. So the key findings from our survey was that there is an overall positive attitude and emotion towards the introduction of AVs in public transport, but each group has specific needs, and understanding these needs may shed light on possible ways to enhance acceptance of AVs in public transportation, like real-time help, practice rides, outreach campaigns, and then auditory and visual cues. So the survey results revealed that safety and kind of the user friendliness aspects of AVs were consistent themes across our 6 groups of participants. So to dig deeper into these themes and expand on these findings from the unique perspectives of each study group, we facilitated 9 online focus group discussions. Each group had 5 to 6 participants. So 8 of the groups were held on Zoom in April 2021, and the 9th group, which was specifically for the deaf and hard of hearing participants, was facilitated over the messaging app WhatsApp. And so we had a total of 53 participants representing each of the groups, and participants were recruited purposefully sampling and received $40 in grocery vouchers at the end of the focus group. So a discussion guide was used by researchers to facilitate the focus group and included screening a 5-minute video of an ongoing AV trial in Singapore to simulate a ride experience. And then for the WhatsApp group, a member of the research team typed each question from the topic guide and put it into the chat group, and then allowed time for participants to respond and discuss more before moving on to the next topic. So it really simulated the virtual focus group discussion as well. Qualitative responses were classified within each group, and top mentions are summarized in the following slide. So this is all about the concerns about safety of AVs. They were a key finding in our survey, and it was also a principal discussion in our focus groups across all the groups. So they all share concerns about the readiness of AV technology for the roads when applied in public transportation. So they want to make sure that AVs can go everywhere a regular bus can go now, and so still working on that. And in particular, they raised concerns about the ability to detect the AV, or the ability of the AV to detect passengers or other road users, also to predict road user behavior and intentions, and then react in a safe manner when something unexpected happens. They're also concerned about the ability to board and alight independently when using mobility devices. So we saw that in the survey, and then again, it came up in the focus group. And they were also unsure about how they, as passengers, should react during onboard emergencies. How will they get out of the bus or out of the vehicle if there's no person to open the door on an electric vehicle? Participants also raised concerns about the risk of physical or cyber attacks on the operating system, or crime on board the vehicle if no service staff is present, potentially putting these passengers in harm's way. So participants also shared their thoughts on how they'd like to interact and communicate with an AV. The AV trial in Singapore at the time featured in the video screen during the focus group, used a mobile app-based interface to book a ride on the AV. So you would select where you wanted to board as well as where you wanted to alight. But once you booked the ride, you couldn't change your destination or your origin. So the participants had mixed feelings about that, because they'd prefer the experience to be much like the existing public bus, where you just flag down a bus at a designated bus stop along the fixed route, and then you have the flexibility to choose where you would like to alight. On the other hand, they could see the benefit of booking a ride in advance, because this would give them an opportunity to indicate if they need any kind of assistance during the journey, like using the ramp, or to make sure that there's space for a wheelchair inside of the vehicle at the time. Participants would also like the vehicle to have the ability to automatically extend the ramp for individuals using mobility aids, so they thought that would make it much more useful for them. And then we heard that consistency is key. So the design of the stop, where passengers wait for the AV, where the vehicle pulls up, the interior configuration of the vehicle, and this will eliminate uncertainty and ensure users know where and how to properly secure themselves or someone under their care. Participants also expressed concerns regarding how the AV will signal its intentions on the road to them and to other users. So they shared that they would like AVs to look distinctly different from regular public buses and be equipped with exterior video and audio indicators to alert others when they are in operation. So what does all of this mean? So consider the range of different mobility and communication needs of potential users when planning and designing infrastructure for AVs, as well as the design of the AV itself. So think about the angle of the ramp and the position of the stop when the ramp is deployed, so that you can facilitate safe rolling on and off the vehicle when using mobility devices, especially if you're unassisted. Ensure the button to call for help is placed at an accessible height. We had several people say that they just couldn't reach where the button was. Also recognize the need for additional time or assistance boarding and alighting, as well as time to settle into the vehicle so the vehicle doesn't pull off before someone is secure or settled in their seat. Provide information and cues in both visual and auditory formats. So when the vehicle is approaching, stopping, doors opening and closing, when the vehicle is moving off and pulling away, and think about how that applies to both the interior and exterior of the vehicle, as passengers are likely to interact with AVs as pedestrians standing by the road as well. Also, assure potential riders by addressing safety concerns and sharing information on safety and trial data. So when possible, act on feedback from riders, and particularly feedback from those who may need some accommodations to improve their experience. Also engage with potential users, prepare education materials, take the AV on a road show in the community, host trial rides, leverage the optimism and curiosity, but manage expectations for the type of AV service that could be offered. And then in conclusion, the study explored the expectations, perceptions, and concerns regarding the introduction of AVs and public transportation among population segments who may need more assistance using public transportation or whose travel needs may be impacted by AVs without the presence of a bus driver. So we identified that across these population segments, the public is anticipating the introduction of AVs with positive attitude and emotion, but they are concerned about various aspects of safety and the user friendliness of the vehicles. So we identified some potential design and assistive technology requirements for persons with varying mobility and communication needs to ensure these AVs are inclusive and accessible when introduced into service. So each group had different needs and different requirements, and understanding the perspective of these users is helpful to ensure that AVs and autonomous mobility services are successfully deployed and adopted by the public when introduced. So thank you guys for listening, and I'm here to answer any questions if you have any. And then I put the full citation for our paper if you want to read more information about that, about the analysis. Thank you.
Okay, great. Thank you, Christy. So one of the questions that came up in the chat box was about the various groups that you surveyed. And so there was a question about whether you considered including individuals from lower socioeconomic groups or, children. So yeah, just if you can comment on that.
Yeah, sure. Yes, so that is one of the limitations of the survey is we couldn't include everyone in this round, and we did include families with children under 12 years old, but we didn't want to include anyone without an adult present. So it was mainly us obviously surveying the parents and their perspective traveling with children. One of the limitations we did note in the paper is that we didn't include people in lower socioeconomic classes or without the language skills to understand announcements and things. And Singapore announcements on public transportation are in 4 languages. And so I think in Singapore, most people are covered, but if you go elsewhere, you might need a different language, then that's definitely something to look into for future research.
Great, thank you. Yeah, and along those lines, there's another question sort of specific to Singapore. So most public transit users in Singapore are accustomed to the driverless metro. Do you have any thoughts on how that would influence willingness to accept AV buses that could make Singapore different from other communities?
Right. So I think the way that Singapore kind of sets itself apart is that the population there is already used to using transit. I mean, 6 million trips per day. Everyone's using the bus or the MRT. The difference with the MRT is that it is fixed guideway, so there's not going to be something unexpected happen. So that's why they're still being very cautious about testing the buses on the roadway, because there's people, other road users and everything like that. So I think in Singapore, people already have a transit mind and the authorities already have a transit mind. So there's a lot of trust there. And so I think that really sets Singapore apart as they're implementing these things. And that's why they're able to do these things.
Great, thank you. And I guess one question that came up was about users outside of those vehicles. So were any of the individuals who you surveyed in your focus group, or were any questions on the survey related to how those AVs might be interacting with, for instance, non-motorized users and the safety implications that could arise?
Yes, we, as part of the general survey that I talked about that was also going on, we did screen for people who were identified as cyclists or pedestrians. And so we did collect data from them. They just weren't included in this paper and this research part. We didn't have enough of a study population that identified that. So we, just for research purposes for this, but we did ask them, and they, to be honest, they kind of had the same sentiment as these groups of people, because they were like, we don't know if it's coming, we don't know how to react, we don't know how the AV is going to react to us. So it was along the same lines. They had some different perspectives as far as crosswalk markings and things like that. But so we did survey them, we just didn't include it in this paper.
Okay, great. So I think we are going to go ahead and move to the next presentation. If you have more questions for Christy, feel free to put them in the chat box, and if we have extra time at the end, we can ask more questions. So Qing, are you here? Qing Shen?
Yes, I am.
Okay, great. So you can go ahead and get into presentation mode while I introduce you. So our next presenter is Qing Shen. Qing Shen is a professor of urban planning at the University of Washington and the director of the university's interdisciplinary PhD program in urban design and planning. His teaching and research areas are urban economics and transportation planning and policy. So with that, welcome, and feel free to get started.
Thank you, Atiyya. Can you hear me clearly?
Yes, we can hear you.
Okay. Good morning, everyone. I'm presenting this paper on behalf of Yiyuan, Wang, and myself. Yiyuan recently completed his dissertation, and he is now busy at his new job with Zillow. This research was funded by PacTrans, the Region 10 University Transportation Center. To begin with, I would like to introduce a basic concept, what we call TMOD, which stands for Transit Incorporating Mobility on Demand. It's similar to what is the more familiar name, that is mobility on demand, or MOD, in that it is also app-based, on-demand, shared. But the distinctive difference is that TMOD is typically initiated by public transit agencies for the purpose of supplementing existing transportation, public transportation provision. Why we initiated this research? We realized that it is a common question for many public transit agencies who are experimenting TMOD to ask this question: is the cost of TMOD service too high? And as an example, several years ago, I supervised a master's thesis who was interning with a transit agency, and he gathered the data about a TMOD service, which indicated that the average cost for first mile, last mile trip to a transit center was $27. Okay, so here's the example. So we thought that to really inform decision-making on T-mod programs, we needed to look at marginal cost. That's a general way of looking at things. Specifically, we raised 3 questions. 1, what are the main components of the marginal cost we are thinking about? Number 2, how can public transit agencies empirically estimate and compare marginal costs of different options? By that, we mean T-mod versus traditional ways of expanding or improving public transportation, such as adding new routes. And then the last question, how do marginal costs differ between traditional transit service and the T-mod? We developed a conceptual framework and then developed the methodology to try to address our questions. So 3 components of this section. Okay, first, an economic theory-based conceptual framework. So here we try to conceptualize for cost at the margin, what we should include to get a good sense of the comparative cost of each option. So 3 arguments. 1, focusing on the marginal cost instead of the average cost for the system. And the argument here is because most T-mod programs are developed to fill transit service gaps in relatively low demand area. So if you compare that with system-wide cost, it's going to be disadvantaged. Not the right comparison. Number 2, we needed to account for both service providers' cost and the users' costs. Number 3, for the user's cost, we needed to not only include the monetary cost, but also all components of time costs. And to complete the conceptual framework, we also need to consider external costs, environmental externality, congestion, accidents, so on and so forth. And the study, to illustrate the framework, we use a T-mod program in the Seattle region called Via to Transit program. And this program was initiated by King County Metro, which is the primary transit service provider in Seattle region, in collaboration with Via, which is a private mobility company. And the maps here show the 5 service areas, which we don't have time to get into detail, but several distinctive service characteristics that we should describe. 1 is the first mile, last mile service. It's an app-based shared. The purpose mainly is to connect the riders to or from one of the 5 light rail stations, okay, operated using minivans, and riders paid only the standard fee. And for the data set we obtained, it covered the pre-pandemic time and with almost 250,000 trips. To take Via to Transit, basically, a typical app, but you need to book the trip, you need to pay the standard fare, and then you need to usually take a short walk to get to the pickup location. Now, estimating economic costs of different service expansion options. So with the via data, we have travel time, including the time stamped for requesting the trip, pickup time, drop off time, origin and destination geolocations, and number of seats requested. And for service providers cost, we work with King County Metro to obtain cost measures. For users generalized cost, then we use a simulation of counterfactual scenarios where via to transit service were not an option. Then if we want to have equivalent travel time, for example, for users, what transit service improvement needs to take place. Okay, and we also simulated the driver alone in comparison. So as example, the left side of the graph shows the via service area. Then we have, in this particular case, two bus lines that also cover this general service area, which we considered as competing options, and we needed to simulate the changed bus frequency in light of VIA's service. We use the SUMO as the simulation program and use the various data. Again, no time for the detail, but the purpose of this simulation is to generate the components of travel time for each option other than via to transit. And then convert afterwards, then convert them into monetary costs in comparable form with the out-of-pocket cost. So 5 counterfactual scenarios, and assuming via to transit was not offered. Okay, so 4 of those scenarios, starting with the King County Metro offer bus services running at current service frequency. In other words, business as usual. Then you have 3 other scenarios, each with increase in service frequency until 5 minutes during regular hours and 5 minutes during peak hours. Okay. Then the last scenario is for those who drive alone. And in that case, the agency provides free parking. And we use a particular date of the covered via service time for the reason that data represents the general service demand and supply. And we use 1 of the 5 service area to illustrate this approach. So here we will talk about several research findings. First of all, this graph shows the distribution of travel time for via to transit and for the other 5 scenarios. And of course, not surprising at all, driving alone has the shortest average as well as the narrowest distribution. And for the transit scenarios, when the service frequency increased to 5 minutes and 5 minutes, then the total travel time on average approximates to via. Other than that, of course, the average travel time is significantly longer. Okay. So with those travel time estimated, we can now estimate cost for the travel times as well as generalized user cost. Basically, we apply the various assumptions that are more or less broadly agreed upon by people who work on time valuation for transportation trip makers, and apply those value of travel time to each of the travel time segment. The simulation we did so far, we assume the opportunity cost of time, if it's fully accounted for, then it's the wage rate for people in Qing County, which is about $36 per hour. Okay, and for service providers cost, we use cost estimation generated by Qing County Metro for their different transportation lines. So in this case, the 2 bus lines with additional frequency, but apply only the portion of the trips that would be added on by the people who are currently taking VIA. And then we also estimated the cost for constructing park and ride facilities based on their recent data. Here are the results of our simulation. Column A here shows the A and B shows the scenario. So the first line shows the VIA to transit, observe the travel time, and the corresponding total economic cost at the margin. So for example, that's 5,278 for that day of record. And then we have the alternative of using driving along plus parking facility. So depending on the lifespan assumed for the parking facility, is it 50 years or 30 years, for example, you see that the economic cost range from slightly over 5,000 to 6,500 about. And then the scenarios of bus services, depending on the frequency of the bus service, the cost range from, in our case, 6,700 to almost 12,000. So what it says is that if our assumed parameters for the simulation and the cost conversion were accurate, then the lowest cost option actually would be driving along if the parking structure lasts for 50 years. And the VIA to transit is the second lowest cost. Or the traditional way of providing transit service at a higher frequency to improve the coverage or a service level would be more costly. And the point, I guess, the important point to make is that in common reporting, discussion, and of TMOD programs, you typically see people focus on column D, that is transit agency's economic cost. So in our case, if we focus on column D, then via to transit the TMOD program, the cost would be for that day, typical day would be 2,500. Compared to business as usual, transit cost that is $1,697 in this case. So the conclusion then would be via a T-mod program would be too expensive. But if we look at more comprehensively, the total marginal economic cost, then you will see in our case, via to transit is significantly lower, even compared to the business as usual scenario. So $5,278 in comparison to $6,729. So just to illustrate that. There are a few discussion and conclusions. First of all, we needed to acknowledge that there could be many different questions to ask with this basic approach. And we can say that in our particular case, the Rainier Beach case, via to transit has a comparatively lower economic cost than expanding bus transit for the average users of public transportation in King County. However, we have not done enough, variations in the assumption and the simulation results. We cannot therefore say that T-mod services, even just via to transit service, necessarily are economically cost effective. Okay. And we also need to acknowledge that while conceptually it's very clear for us that external costs need to be considered, the economic costs we measured do not explicitly account for those externalities. As I said, we needed to say also that based on existing literature, for example, Perrine and co-authors, they estimated the external costs of driving, and we adjust those estimated costs for inflation. If we include those, then the amount added for that day would be $201. Okay, so not going to change our conclusion in significant way. Actual small switch between via transit and driving along with 50-year lifespan parking structure. But we also know that the estimation of externalities change over time. We have not looked at what would be the worst scenario if, for example, CO2 emission fee becomes significantly increased with acceleration of climate change. So acknowledgement. And there are other factors we needed to acknowledge. For example, for driving alone, yes, we show the cost of it, but that does not mean that could be a realistic scenario for everybody, because barrier to car ownership is a real barrier. And we cannot just say, well, if that's the cheapest one economically, everybody could just use it. Not that simple. And for certain transit stations, actually constructing park and ride facility is not realistic. So those are acknowledgement of limitations. So to summarize, it's a conceptual framework based on economic principles. I think we clarify the confusion in terms of how we should look at the cost of T-mod services. And for that purpose, we developed a simulation model for empirical estimation. We believe that jointly.
Just a reminder that our time is
yes,
up
this
for the
is the last.
so we could just wrap up.
Yeah, this is the last. Okay. So we believe that we have this tool that we can build upon to be practically useful. Okay. And in our case, the conclusion is clear, but that's not necessarily generalizable in terms of conclusion of the policy decision for other cases. So with that, thank you
Great.
very much.
Thank you. Thank you, Chng. So we are a little bit behind schedule, so we'll just take one question from the chat, and then at the end we can come back if we have more time. Someone noticed that on the summary table of costs, the average vehicle occupancy was just barely greater than 1. So I'm just wondering if you can speak to that a little bit. Yeah.
Yeah. So in an earlier publication, actually, we, Yiyuan and I, we were the co-authors, we raised the notion of deepening sharing. So there, the key idea is to increase occupancy as a critical goal for shared mobility. Now, in this case, first of all, it is a little bit low, so kind of unfortunate. But also, the calculation is such because the whole trip segments carries different passengers. And in some cases, I assume that actually some passengers may request returning, trips in other direction, and the drivers cannot wait for getting more people on the vehicle before make the trip. So I think because the on-demand nature, and that's the explanation for the lower occupancy rate.
Great, thank you, Chng. So we are going to go ahead and move to the next presentation. Matt, Dean, if you can go ahead and get your slides up, I will go ahead and introduce you.
Great, thank you.
Great, thank you.
Okay, so Matt is a PhD candidate at UT Austin's transportation program and works with Dr. Kockelman. He studies optimization-based control strategies for electric vehicle fleets and joint transportation and power system modeling. And today, Matt will talk about research that uses publicly available Chicago ride-hail trip data and spatial econometric techniques to understand the demand and factors leading to trips with sharing authorized. So go ahead and get started, Matt.
Thank you so much, Atiyya. I'll get right into it. So we should all be familiar with TNCs by now. We have Uber and Lyft in North America and Europe, as well as Didi and Ola in Asia, Journey and Bolt in Africa. And of course, they are different than taxi structures, mostly by owner-operator structures who owns the vehicles, whether they have the ability to set their own schedules and routes. And we have data that shows that in 2017, 8% of respondents had taken a TNC in the previous month. And with vehicle advancements in automation, new players like Cruise, Waymo, or even Baidu could own and operate their own vehicles and lower per mile costs by eliminating drivers. I'll try to speak a little bit loudly so that you all can hear me. Pooling or shared rides took hold later as demand for more affordable trips increased. And a study of 1.8 million sharing permitted trips in Toronto found that about 52% were successfully matched. And since these unmatched shared trips are just as bad, if not worse, because cheaper fares may attract more riders, the key to unlock congestion and sustainability benefits requires a higher match rate. Of course, driver complaints about low customer ratings due to inefficient routing and pairing has led to some gradual changes. So Uber is capping detours at 8 minutes, and Lyft is restricting a shared ride to just 2 separate passengers. And post-COVID, Uber is now returning their shared service in 9 US cities, and Lyft is returning it back in 7.
Matt, sorry to interrupt. If you could just speak a little louder, that'd be great. Thank you.
I'll try my best. This study is focusing on shared ride-hail trips since most prior studies have looked at ride-hailing in general, and we already have a good idea as to who uses those TNCs to get around the purpose of that trip and what modes otherwise would have been used. But we don't know that exclusively for shared ride hailing. And before this research, I had found 5 studies before that had examined pooling with various methods and scopes. So that first row from Chen et al. In 2017 used DD trip data to build a classification model, so pooled or not pooled. And then the subsequent paper in 2018 looked at results from an in-app questionnaire to hitch and express riders, which is more akin to reservation-based slugging or carpooling, as opposed to true on-demand ride hailing. The third study, Li et al. Proposed processing DD trip data to understand average trip detours and travel time reliability, and a regression was used to estimate delay of shared rides. The next study looked at a survey of DD pooled riders to get mode shift data, understand how TNCs impact vehicle usage, and to capture vehicle purchasing plans. The fifth study that I'm showing here used the Chicago trip dataset and bin rides between pickup and drop-off census tracts. And using spatiotemporal sociodemographic variables, they were able to predict the sharing and OD pairs. And then the last study here by Kong et al. Looked at Austin, Texas respondent data to develop a GHDM model in which nominal, binary, and ordinal data are considered simultaneously, and they predicted who's more likely to use a pooled service. And so none of those prior papers had used spatial econometric techniques, which may be warranted, considering that the spatial component of a trip is just as important, if not more, than the temporal component. So as a result, we looked at the spatial lag or error models for a fixed month to try to keep seasonality and other temporal changes to a minimum. And then we looked at linear panel techniques with or without accounting for a spatial term. And the goal of including this spatial component is to improve model estimates by possibly avoiding biased and inefficient estimators, just depending upon the underlying spatial processes at hand. And this should hopefully reflect the contribution of a nearby tract values in the model. And so other common models that may be that you guys may be aware of is a geographically weighted Poisson regression, spatial lag, and the spatial Durbin, which is used in subsequent papers after mine. So given the desire to both understand not only the count of shared trips, but also the proportion, I created 2 separate univariate models. And the top half shown in orange is just looking at the non-temporal portion of the study from January 2019. And then the blue bottom half is looking at the temporal analysis by month for the year of 2019. And the error term for the linear panel models could be considered either constant across census tracts or fixed effects or randomly distributed, so random effects. We test that using the Houseman test. And then we also considered the spatial linear panel model as well to consider how spatial effects may be present in this linear panel data set. So before I go into the model specifications, I'll present kind of what the Chicago data set has available to us, as well as how did I get demographic and built environment data. So Chicago provides trip locations by pickup and destination track, and then they disaggregate data by going to the nearest quarter hour for start and end times, as well as fare to the nearest $2.50. But the trip duration and distance are kept and preserved. I also looked at demographic data from the ACS at the pickup track level, as well as built environment to understand how those characteristics could, I guess, tease out shared pooling. More trips here in Chicago are taken on the weekend than weekdays, as is common in other locales. And within the workday, there are clear time of day morning and evening peaks, with the evening sloping down more gradual than in the morning. As far as those duration and distance components, the majority of Chicago trips are short. There is an exponential decline in trip duration roughly after the 10-minute mark, with very few trips in Chicago lasting over an hour, and that's not shown. And then similarly, over half of all TNC trips are under 3 miles. Looking at our X variables, there's significant spatial variation by pickup track. So here I'm showing percent zero vehicle households on the left and percent non-white residents on the right-hand side. The next slide shows our residents with at least a bachelor's education, and then the population weighted centroid distance from transit. The proportion of shared rides by pickup track also reveals a stark geographic divide. Southside neighborhoods generally have higher sharing proportions compared to the CBD in North Chicago neighborhoods. And then the demand magnitude is reflected in this plot where the CBD and the O'Hare census tracts have a higher average daily count of shared trips, to no surprise. So going into a simple LLS with the proportion of shared rides to total rides by pickup track, we see that built environment variables on the bottom can be good predictors, at least at the 10% significance level. On the other hand, trip specific and most socioeconomic variables are statistically significant at the 5%, 1% level. So overall, we're seeing that a proportion of shared rides by pickup track increases with trip lengths. Census tracts with a higher median household income were less likely to share rides, likely because those residents already have more discretionary income for private trips. Tracts with a higher percentage of unemployed residents, non-white residents, and young people in zero vehicle households also had higher sharing proportions. And urban areas with a high population density and density of pet infrastructure also had higher ratio of pooling. And this may be indicative of areas with underlying demand for ride hailing, but maybe also suggestive of possible mode substitution of would-be active transportation users. Looking at SAR and SEM models, I first looked at Moran's eye test with different spatial weight matrices and found there was significant spatial autocorrelation. And then a subsequent Lagrange multiplier diagnostic for spatial dependence confirmed this conclusion. So I went ahead and went with these two models. The SEM has statistically significant variables at the 90% confidence level, except for that distance to transit variable, as did the spatial autoregressive model, but the SEM has a slightly better fit as shown by the log likelihood and AIC statistics. When yearly trip data was considered, we noticed some gaps in data collection around February and then the first half of May. And so if you look at an unbalanced panel data set with nearly 780 census tracts, you end up with over 232,000 daily observations, ranging from at least 23 days up to 313 days. And so with this linear panel model, I'm considering the base OLS spec and to test for fixed effects and random effects. And interestingly, the Houseman test implied that a fixed effects model was a better choice. So then I developed a time fixed effects model to account for the variation in months. So the interesting finding here was that there was an increased magnitude in the monthly indicator variables shown on the right. So as the year progressed, there was a portion of shared trips declined. So we don't know why this may be the case, but the earlier Toronto study suspects that changes in matching algorithms may have pushed riders to pay and avoid poor matches. And like the proportion model, this one looks at just the count of shared ride hailing by pickup track. And so increases in average trip distance and duration led to more shared trips. There are also more trips occurring in the afternoon and evening hours of the weekend, likely because of more social and leisure activities. And then areas that have a high density of ped infrastructure would be more conducive for active modes, but had fewer shared trips. So this is for the January 2019 subset. So possibly wintry weather discouraged those active modes and nudged people into a more direct solo trip. The further the population is from transit, the less likely people were to have taken this shared mode. And interestingly, neighborhoods with longer work commutes were less likely to have taken a pooled ride. And so this work commute variable can capture areas where residents can't afford to live close to their jobs, or areas where privacy-minded individuals reside because of the desire to live further away from work in less traveled neighborhoods. And so these two variables can go hand in hand, and that transit deserts and neighborhoods with long commutes are less likely to use shared modes, be it transit or shared ride hailing.
Matt, you have about 3 minutes remaining.
Great. And here we're showing the specs of the preferred random effects model through generalized moments and then through maximum likelihood with that serial error correlation and spatial lag dependent variable. And so I found that there is nearly no random effect truly present. And if you remove that random effects assumption, but keep those terms, the magnitude and the signs of the coefficients largely don't change. So if you were to use a spatial linear panel model, the spatial Hausman test finds that the random effects through generalized moments is the most appropriate one. And so moving right away into those summary results, there are key takeaways here in that we confirm the results of revealed preference and intercept surveys of shared ride hail passengers by linking census tract data to trips, even though there's a caveat here, we can't be sure that those riders are indeed the passengers. Second is that demand for shared rides, both in proportion and count, fell when there was a high density of pet infrastructure. And this is true even after accounting for other covariates. And the higher sharing was found when residents are closer to transit service. And so for long distance trips where transfers may dissuade travelers from choosing it, operators could promote sharing to increase AVO, decrease passenger mile emissions, and lessen congestion. And finally, tracks with a higher share of young people increases the proportion and number of shared ride hailing trips. And since millennials are more educated, but also more in debt than previous generations at their age, there may be value to instilling shared travel benefits to unlock long-term benefits, whether that's in high occupancy TNCs, buses, trains, or SAVs. And lastly, there were a few existing papers that reflected spatial autocorrelation that comes with almost any kind of intra-regional travel demand data. So I just show some straightforward improvements to OLS models that other people may consider in the future. And as far as those panel or linear panel models go, there are some significant trade-offs as far as computational memory requirements. So you either trade off in a large number of census tracts or temporal observations. So thank you for listening. Happy to take a question.
Okay, great timing. Unfortunately, we're running a little behind schedule, so we're going to go ahead and move on to the next presentation. And maybe if you can take a look at the chat box, Matt, for some of those questions. So Yantao, please go ahead and share your screen, and I will introduce you. So Yantao Wang is a postdoctoral researcher at the National Renewable Energy Lab. He received his master's in transportation from Imperial College London and his PhD in transportation engineering at UT Austin. His research focuses on traffic simulations and travel demand forecasting, especially anticipating the impacts on sustainable transportation systems from emerging technologies. So with that, please.
Okay, hello everyone. So this is work that I did a few months ago when I was a postdoc at UT Austin with my colleagues Perrine and Kockelman. This project was for the Texas Department of Transportation. It's like explores the impact of both automated vehicle, passenger vehicle, and trucks on the long distance travel across the United States. So like for the passenger model, we have another session. I think it's pretty like the same time at another track. It's the last presentation. But this part is like I am introducing the freight part. It's not very related to shared mobility, but it's just how we anticipate the automated trucks flows to be across the United States. So the automated trucks, they are expected to lower the crash rates and bring some environmental benefits. Things like we have a better control of the vehicle, and also we can accelerate and decelerate smoothly. And we also expect lower shipping costs and delivery times, because we don't if they are fully automated. We don't need to have drivers on board, but although we are still expecting like people on board to take care of some of like the administrative work. And also it has like faster delivery times because those trucks can run 24/7 and we don't need to coordinate with drivers like working schedules, so we don't have to rest at night. And also they can facilitate the last mile delivery. In 2014, trucks carried about 2,000 billion ton miles of freight around the US, and it is over like one third of the US ton miles. And if we are looking at the like the value transported or ton, like the weight transported, they're more than like one third. So in this work, we use two data sets. The first is the trade flow from fast analysis framework version 5, which we call the FAF5. And we also have the industry by industry transaction tables and regional purchase coefficients, which we call like the input output table from implant company. And the way we explored the like impact of automated trucks was to disaggregate them to over 3,000 domestic counties and check the trade flow between each commodity. So we had a mode choice and origin choice model estimated with FAF5 data set. The mode choice model has like only has two modes, the truck and rail. And we also have the origin choice among 135 zones, and we further disaggregate them to domestic counties. And the model estimations, they are fed into the random utility-based multi-regional input-output model to get the trade flows across the different industries and between those domestic counties. So these are the like industries, or we call the economic sectors in our ROM-RAIL model. Since we have the input-output table from implant and also like the SCTG freight category from FAF5. So we did a matching across all the industries, and this table shows how we did that. And for the mode choice model, we considered the cost and time in the utility function. The cost is related to the distances. The truck distance, we extract them from the 2010 our journey estimates. Our journey model is a long distance travel demand model. We obtained the passenger travel or the highway scheme from there. And we also did an average estimate from FAF5 to get the real distances. And for the travel time, we assume the 45 miles per hour highway travel time for truck. And also if the on-road travel time is over 10 hours, we assume another 14 hours to accommodate the working schedule of the drivers for the human-driven scenario. And in the autonomous vehicle scenario, we'll get rid of these 14 hours. And for rail, we have 30 hours dwell time at rail stations, and we also assume an average rail speed of 21.72 miles per hour. The travel times, so when we estimate the models, we ran into some like coefficient issues. So we further transform travel times from hours to minute and take the natural log of it to maintain a reasonable scale for both truck and rail. And these are the utility equations, and we had the alternative specific constant for rail utility. And for origin choice model, it is for industry purchases resulting in freight shipments. We distribute them across the like 132 zones based on FAF5 data. And based on the utility or parameter estimations, we fit them into ROM-RAIL model so that we can better distribute them or disaggregate them to US counties. So we had two variables in there. The first is about like the transportation utility, which we use the log sum of the mode choice model. And we also represent the traction of the origin by the log of the population in the origin zone. And we use the Polo package to iterate code for this origin choice. This is the model implementation. So there are some like key equations in there. They are like formulated as a 6-point problem. So the way we solve it, as I'm showing here, is just initialize the variables as 0 and iterate until it converges. So the input that we have is the export demand and also the travel time and travel cost for as input for the utility function. We initialize the sales price and domestic flows as 0, and then we kind of do an iteration of distribute the export flow based on the utility. We sum them up as production, and we use the input-output table to transform them to consumption in each zone. And we also distribute the consumptions across the domestic zones. And after this gives them a domestic trade flow pattern. And we, based on the trade flow pattern, we calculate the input cost of the transportation. So we get an average transportation cost, and we further use the original purchase coefficients to transform them to sales price. The sales price goes back to the utility function as in part of the utility considerations, and continue with this whole iterative process until we get the equilibrium trade flows for each commodity across all the counties, and we can also get the sales price and the mode share. So what I mentioned was for the human-driven truck scenario, or the general framework of the problem, and for the automated truck scenario, we had a autonomous truck all nested on the truck, and yeah, that's the mode choice structure that we had for the truck scenario. So for the base case, we had the export amount as 1.06 trillion in 2017, and that led to 11.1 trillion domestic freight flow, and the trucks took about 83% of the ton miles, while the rest are the rail. And yeah, and the automated truck scenario has another mode nested within truck. And we had the A-trucks operating cost we assume to be 50% of A-trucks, either because we don't need any trucks, we don't need any truck drivers, or they can just stay in the vehicle and perform other tasks. So these are the assumptions, and here I'm gonna present a few results. So the first is the before and after A-truck scenario, and in terms of the change in truck and rail in ton miles. A-truck introduction caused an increase in both domestic and export truck ton miles for all trip distances, especially 1,000 miles to 1,500 miles. And export rail ton miles shift to trucks, but domestic rail share still increases for trips between 1,000 and 1,500 miles, or shorter than 500 miles. And human-driven trucks mode share drops as the distance increases, but it's mostly right after 250 miles. But the autonomous trucks share is quite stable. It's about 50% across all the distances. Now we are looking at the value transported, but we're still adding more results to this project. So we are further look into the ton miles or the ton transported by each mode. For the rail, the mode share is low at distance shorter than 250 miles, but it raises to about like 20% after 250 miles. And another thing we looked into was like the impact of autonomous trucks overnight time savings. So the drivers, so for the human-driven trucks, the drivers need to rest. But for autonomous trucks, we can just keep driving overnight. So as I mentioned, we assume an extra 14 hours of non-driving time for every 10 hours of like human-driven truck on road travel time. So this for this we provided a comparison of like two autonomous truck scenarios. One where we reduce the cost, the operating cost by 50% and also eliminate the overnight time savings. But we compare it with the case we only have the cost reduction. So this gives us like how much more value of freight or ton miles of freight that we can transport, considering the overnight travel time savings.
Yantao, you have 3 minutes remaining.
Yeah, it's going to the end. So if the travel time saved is taken into consideration, it attracted like 25% more value, 25% ton miles transported, and like 15% more value transported by autonomous trucks. And that happened at between 500 miles to 750 miles. And later, the dropped for longer distances after 1,500 miles. So in conclusion, we predicted the trade flow across the US. We estimated the origin choice and mode choice model, and we fit the parameters into the round mode. We had increased ton miles transported by truck across all trip distances, especially for trips that are between 1,000 miles and 1,500 miles. A human-driven truck's mode share is slightly higher than autonomous trucks for shipments shorter than 250 miles, but autonomous trucks, they are preferred for trips longer than that. And also when we take the overnight time saving into consideration for autonomous trucks, we have the benefit takes at 750 miles at an increase of 25% for the ton miles transported. Yeah, and that's about it. And yeah, if you have any questions.
Great, thank you, Yantao. So if anyone has any questions, please go ahead and put them in the chat box. We are going to go ahead and move to the next presentation. So Matt Bruchon, are you here?
Yeah, I'm here.
Okay, great. So let's go ahead and get. So Matt Bruchon is a postdoctoral researcher in Carnegie Mellon's Vehicle Electrification Group, where he completed a PhD in engineering and public policy. He investigates the environmental and social impacts of transportation and energy use and assesses policy interventions using optimization, econometrics, and machine learning. Prior to this, he completed MS degrees at MIT in technology and policy and electrical engineering and computer science. So with that, please go ahead and get started.
Thanks, Atiyya, for the introduction. I'm excited to share our work today. So the paper that I'll be presenting today was co-authored along with Connor Forsythe in mechanical engineering at Carnegie Mellon and corresponding author Jeremy Michalek, also at Carnegie Mellon. And before I get into our core research question, I wanted to start with a slightly more basic question, which is who pays for your car ride? So for each mile of vehicle travel that happens, there are certain costs incurred. The numbers that you can see on this slide are estimates that we pulled together from various sources in the literature for the study that I'll talk about today. So these are specific to Chicago and specific to the year 2019. But for each mile of driving, there are certain private costs, such as fuel, maintenance, depreciation, and these marginal costs sum to about 27 cents per mile. But on top of those costs that are paid by the driver or perhaps the rideshare passenger, there are also a set of external costs that are unpriced. And so throughout this talk, when I say external costs, I'm referring to those additional societal impacts that we don't necessarily force anybody to pay. So these include things like congestion, things like emissions, and things like crashes. So the chances of all of these things go up for each additional unit of vehicle travel. And these are not small costs at the per mile level. They sum to around 22 cents per mile in our estimates. Scaled up to society, these costs are even more considerable. So by one estimate, lost time from congestion costs up to about $100 billion per year. The transportation sector is the largest sector of GHG emissions within the US, and it also leads to around 20,000 pollution deaths per year. And on the crashes front, we have in the US around 36,000 annual deaths from vehicle crashes, and about 20% of those are non-motorists, such as pedestrians. So there are these considerable external costs associated with car travel that aren't necessarily factored into the driver's or the rider's decision-making. And within that broader sphere of transportation, on-demand ride-sourcing services, such as Uber and Lyft, are a fast-growing share. So in 2019, Uber served around 7 billion rides. At the city level, in a place like New York City, pre-COVID, we saw about 600,000 riders per day. And in places like San Francisco County, which has a relatively high usage level for Uber and Lyft, these services represent around 13% of total vehicle miles traveled, and by one estimate, about half of new congestion from 2010 to 2016. And we've started to see, particularly at the state and city level, some efforts to regulate the use of ride-sourcing fleets. Things like congestion fees in New York City, Chicago, and San Francisco. And one possible lever that we have to reduce these externalities is the use of ride splitting, which I'll refer to interchangeably with ride pooling. This is services such as Uber Pool or Lyft Line. So we'll hear a lot of talks at this conference about vehicle electrification, and that's one very valuable policy lever that we have to reduce these external costs. But electrification alone can only do so much. One reason for this is that there are supply chain emissions, and there are also power grid emissions that will still occur. But another reason is that even if we could make the grid zero carbon, we would still have these other traffic-related externalities that I alluded to, things like congestion and crashes, which by some estimates are 70% larger than emissions external costs. And to chip away more at those traffic-related costs, we need to think about VMT reductions. And one key approach to do that could be ride splitting. So the question that we ask in this study is whether those unpriced external costs are distorting the use of ride splitting services. And if they are, maybe that represents a substantial market failure. And we test this hypothesis or this question by running separate test cases with and without those costs being paid by the ride sourcing service as a tax. And if we see a change in operations when those additional external costs are paid, then there could be a case for some form of public policy to encourage more ride pooling. And so the method that we use is we apply historical ride sourcing trip data, specifically from the city of Chicago, and we optimize vehicle routing as well as ride splitting choices to minimize private costs. We do that next with the same model and the same method, but we add into the objective function the external costs of air emissions and traffic. And we compare across those two scenarios the vehicle routing and the resulting external costs across a range of scenarios. And so just to put all of those costs that we include on one slide, you have a range of private costs that generally tend to tilt the decision making towards more sharing. So you think about things like fuel costs, and if ride sharing or ride pooling will reduce VMT, then it will also reduce those fuel costs. So this implies that the fleet already has some incentive perhaps to do some level of ride sharing to minimize their own private costs. And when we add in these external costs from things like emissions and things like congestion, each one of these costs should also tend to tilt the equation in favor of more ride pooling. The main costs that would tend to discourage ride pooling, number one, are traveler wait and delay times. So if you're sharing the ride with somebody else, there are going to be delays for your pickup reps, and there also will be detours along the route. The second cost that should discourage ride sharing is the loss of privacy that you have when you share the ride with a stranger. And for these costs, we borrow basically a median estimate across 3 relevant studies from the literature. One of our challenges is that with this style of optimization model, we can't easily simulate a full representative calendar year, for example. So we need to pick a representative week. And at a high level, the way that we do that is apply machine learning. First, we cluster demand patterns to determine a set of kind of representative sub-patterns. And so that's the first set of curves you see here. And these represent things like weekday commuting versus the demand patterns of going out to the bar on the weekend. So we use that to develop a set of 8 covariates. And then we find a week that has the most typical volumes across each of those 8 demand patterns or those 8 covariates. And again, for tractability, what we do is we process that representative week in 5-minute batches of ride requests. So next, I want to briefly go through some of the technical method. And I have it illustrated here on just a representative street grid. And on the right-hand side of this slide is the slightly more complex version of that grid, where we translate it into a graph to optimize for. And I should add that this method is adapted from a 2017 paper by Alonso Mora et al. And so essentially what you have is this street grid of, in this case, just 4 riders who are requesting rides. The flags on this plot represent the destinations that they're hoping to get to. And you also have a couple of cars to serve these passengers. And so the first step is simply to find the minimum cost path to serve each of these passengers with each potential car. And if that car is feasible for that passenger, we add it to a graph of potential options. So it's very easy, for example, for car number 1 to serve passenger A. So we would add that as an arc to this shareability graph. And that arc would have an edge weight that's equivalent to the routing costs. We repeat this for a bunch of different combinations of cars and passengers until we've fully built out this graph. And once we've built out that graph, our second step is essentially to scale that graph up to pooling rides. So what we do in this case is, let's say we've already determined that car number 1 can serve passenger A. Next we say, given that matching, who else could we possibly add into this to form a ride pool? Taking passenger C as an example, passenger C's pickup location is already more or less along the route for passenger A. And so that's a relatively easy ride pooling combination. So we add all of these feasible ride pooling combinations into this same graph that we will eventually optimize over. Our optimization model itself is simply minimizing the costs of operation, including a reward for all of the requests that are served. So basically the fleet will serve as many passengers as it possibly can within each 5-minute window. And given that, it will minimize the routing costs. So this could give us, for example, a pairing of passengers A and C into car 1, and a pairing of passengers B and D into car 2. A second step, once we've completed that optimization process, is that we rebalance the fleet. So at the end of each 5-minute window, you might have some vehicles that were unused, and you need to decide where to move those vehicles to meet your next set of demand. On the other hand, it's possible that if demand forecasts were not accurate, or if there just is a lot of demand in a certain time window, you could have some unmet trips in that first 5 minutes. So then we need to rebalance vehicles to meet those unmet trips. We have 2 versions of this second stage optimization. In one version, we're focusing again on efficiency basically and minimal cost routing. That'll be the results that you'll see today. We have a second version that is still in progress where we instead prioritize equity, and the objective is essentially to maximize the welfare of the worst off neighborhood. So next I want to go into the results. What you see on this plot here is showing the total costs on average per trip. And the bars are colored here to show the different cost components. So it includes not only operations costs, but also the costs of lost traveler time, as well as the costs of sharing related to privacy. So the first case that we run, there is no tax to internalize external costs, and there also is no use of pooling at all. So this is a 100% solo ride fleet. And in that case, your total private costs sum to around $12, and your total external costs per ride sum to around $6.
Matt, you have about 3 minutes left.
Okay, thanks. So a total of about $18 per trip. Next, we consider tax where we internalize those external costs. And there is very little impact in this case. That's because we still can't pool rides in this particular scenario. So next, we do enable optimal ride pooling. And what we see in this case is that costs do go down substantially. Private costs fall by about 4%, so the fleet can save money simply by doing some ride pooling to the tune of about $30 million per year. We also see that external costs, and again, this is pollution, climate change, and traffic, these fall by about $86 million per year. So these are some substantial reductions in costs that are enabled just by allowing ride pooling. On the other hand, we see that further taxing those external costs doesn't do very much additional as long as the fleet is already allowed to pool rides together. So essentially what we see is that in the baseline business as usual case, there are already, to optimize costs, just over half of rides that use ride pooling in some degree, and that goes up by only about 3% when you add a tax. So our top level takeaway here is that ride splitting is very often more efficient than solo rides. It does appear to have a lot of value for these fleets in reducing VMT and costs, but it isn't obvious that there's a case for policy here to correct a market failure. Having said that, our status quo case does have about 2 times more ride splitting than the Chicago dataset actually shows. One reason for that might be that there are disincentives beyond cost that could discourage pooling in real life. So it's a lot harder just to coordinate your fleet and to manage operations when you're doing a lot of ride pooling. So we're also considering additional sensitivity cases to calibrate that sharing percentage. And finally, just a couple notes of context. This market failure that I discussed, it's not unique to ride sourcing. It also does pertain to private vehicle use. We focused on cost minimization, but there are other grounds for policy, such as equitable transportation access, And finally, I know this is preaching to the choir in this audience, but more robust data from more cities beyond Chicago is needed so that we can apply these kinds of methods to other cities too. So thanks for your time.
Great, thank you, Matt. So I think we have time for one question. Deborah asked, noted that she did a similar analysis of private car cost per mile and is asking if you can share what data you used to calculate your estimate.
Sure. Sorry, was the question sharing costs per mile specifically? Or was it just all costs?
Yeah, I think it was all costs. Yeah.
Okay, so we pulled it together from a variety of sources. I'd be happy to talk more offline about those data sources. Some of them came straight from the literature, things like, value of travel time. Some of them were more region specific, things like fuel costs in Chicago. But I'd be happy to talk more about those offline.
Great, that sounds good. And I guess just one more question. So in your equity objective function, how did you define the worst off neighborhood?
Yeah, so essentially what we use there is the ratio of available cars, like cars that currently have a seat open that they could serve somebody with, the ratio of those available cars to the number of upcoming ride requests. So basically we're trying to minimize the supply shortage in each neighborhood, basically.
Okay, got it. Thank you. Great. So if you have any more questions for Matt, feel free to go ahead and put those in the chat box. And Jeremy, you can start sharing your slides, please. So Jeremy Michalek is a professor of engineering and public policy, professor of mechanical engineering, professor of civil and environmental engineering, and director of the vehicle electrification group at Carnegie Mellon. So basically, he's very busy. So go ahead and get started.
Sure, thanks so much. So this talk is also on a paper that the previous speaker, Matt Bruchon, led, and Matt has recently graduated, and the other authors included Connor Forsythe, Charlie Andreasen, and Kate Whitefoot. And the question we were interested in here is, Chicago made a change to the way they tax TNC rides in order to encourage more ride pooling and to discourage riding during peak hours. And we wanted to see if we could figure out whether that tax really worked and whether it had the intended effects. So we're interested in this question because congestion is an enormous part of externality costs, maybe $100 billion a year in the United States. And there's evidence that ride sourcing really contributes to it. And one estimate, the majority of the increases in congestion costs in San Francisco from 2010 to 2016 were due to ride sourcing. And so a number of cities have started to enact policies that discourage behaviors that increase congestion. In Chicago, the majority of trips have an origin or a destination that are in or close to downtown, and that's where most of the air pollution damages happen because of high population density. But if you look at who's pooling, the rides that opt in for pooling are mostly not downtown. They're mostly in the outlying areas. So what Chicago did before January 2020, they applied a base fee to all TNC rides of 72 cents, regardless of the time or the location. And what they started doing in January 2020 is, first of all, they increased the baseline fee schedule to $1.25. And they gave a discount to that if you pool the ride. So it's only 65 cents if that ride was opted in for pooling, even if it didn't actually get pooled. And then they added a differential treatment for what they call the peak demand hours. It's between 6 a.m. and 10 p.m., which is the whole day, Monday through Friday. If you're traveling to or from one of their key regions, which include the downtown zone, the airports, Navy Pier, then you get a higher fee added to your ride, and that discount is larger when you share during those times. So because there's this differential treatment, we can use a difference in difference approach to try to isolate the causal effect of this policy on ridership. And so we're looking at outcome variables that include daily rides, which we log to get percentage changes. And then we're looking at the percentage of those rides that opted into ride splitting, or were actually matched with another rider. And we're modeling those as a function of treatment. And in our case, the treatment is whether that ride was subject to the elevated fee. So whether it was down in one of the downtown or other zones during the peak hours. And then we have time and route corridor fixed effects. And to, as Matthew was talking about in a couple of talks ago, we wanted to also account for spatial correlation issues that could potentially bias our terms. So every travel corridor will be affected by changes in nearby corridors potentially. So for example, if you had an increase in demand from downtown to the airport, that might result in more P&C vehicles available at the airport, which could reduce prices or wait times for rides from the airport to other places. And so we include some spatial correlation terms in order to account for that and reduce the bias, allowing the outcomes along corridor I to be dependent on the corridor J. And we use a spatial correlation matrix that is based on the proximity of those corridors. When we look at the time series data, we do see what looks like the effect we might expect. So not downtown rides, ridership seems to drop more after the surcharge is introduced than non-downtown rides. And similarly, downtown percent of rides pooled seems to increase more after the surcharge than rides pooled in non-downtown rides. And when I say downtown, I'm talking about all of the treated areas, including the airports. So our model would be able to estimate how much of the magnitude of this effect. Before running the model, we want to group our travel corridors, and that's because a travel corridor in the resolution that we have in the Chicago data is either between two census tracts or between larger neighborhood zones. And some of those corridors between two census tracts have a lot of traffic and others have not so much. So there's a big spread in how much activity there are in these travel corridors. We want to group those travel corridors into similar sized groupings so that when we talk about percentage changes across different groups, they have the same meaning, that they're talking about the same number of rides. And so we use a machine learning technique to try to group these travel corridors into similar sized groups while making sure that the travel corridors themselves are geographically similar to one another. And we, as a sensitivity case, we also look for a case where we ignore the geography entirely and just put them into the most similar sized groups that we possibly can. So here's an example of what that would look like. One of our groupings is the one on the left, where there's a set of different origin and destinations in red that get grouped into the same group of corridor, the same corridor, that all represent sort of northern trips that are moving from west to east in this case. Or the blue on the right are trips that go from kind of the northwest of downtown up north toward the northern suburbs. So when we run the model, what we find is that relative to other corridors, the corridors that are subject to these higher surcharges have a bigger drop. The ridership drops by about 8% more in those corridors than it does in the ones that weren't treated with a high surcharge. And there's an increase in pooling, about 4% increase in people opting into pooled rides, and about a 3% increase in how many of those rides actually get matched with other travelers. So it looks like Chicago had exactly the effect it intended. It dropped the ridership in the target zones, and it increased rates of opting into pooling and actual pooling in those same zones. For each of these outcomes, we do have a large spatial autocorrelation term, and that suggests that these effects aren't just the direct effect of the tax on that one corridor, but also have effects that on neighboring corridors or through neighboring corridors. We do some sensitivity analysis. This is one example. We looked at the same results when we ignored geography entirely. So we group those travel corridors based only on trying to get the most same size that we can and ignoring the geography. And we don't use the spatial autocorrelation terms in the model. And we get results that are really similar, a little bit larger in magnitude, but basically similar. So we see some good robustness to our results. So bottom line is, it looks like Chicago's tax did have its intended effect. Rides downtown and the treated zones decreased more than other zones after the tax was instituted, and the willingness to share rides increased. We would like to do more research to understand what the net impact of all these changes were on congestion. It's a little more tricky to do because we don't have congestion data directly. We do have vehicle speed data from the TNCs on their own routes, and we have speed data from buses, but there's a lot of challenges to making the method work for that, so it's something we're still thinking about. And then we also want to put this in context. We only estimate here the differential downtown effect. So, for example, the tax across the board was intended to encourage more pooling, and if pooling increases in other zones and it increases even more downtown, what we're measuring here is the difference between the two. There may be an overall effect that's even bigger than the differential effect we're able to measure with this difference in difference. Then the other thing to mention is they instituted this policy in January 2020, so there's only a couple months of data before COVID hit. That amount of data is sufficient for us to make these claims, but things have changed post-COVID, and the degree to which these policies would have the same effect in a post-COVID world, we can't comment on for this study. That's all. I'll be happy to take questions.
Great, thank you, Jeremy. Are there any plans to follow up doing a similar study with post-COVID data?
Yeah, the trouble is that things aren't stable yet. So we can look at post-COVID data, but things are really changing. The thing that was unique that we were able to identify here is we had a pre-policy period where we could see the patterns, and then the policy hit and we could see how the patterns changed. So if we're going to look at a post-COVID period as ride pooling is becoming available again, we wouldn't be able to identify these kinds of effects unless there was another change in the policy. So if that happens, you can bet we'll be on it.
Right, makes sense. Okay, so we have a little bit of extra time, so I'm thinking we can actually maybe have some discussion from the audience members. So if you do have a comment for Jeremy or any of the prior speakers that you'd like to ask yourself, go ahead and put your hand up, and maybe we can unmute you and have just a little bit of time at the end here for some discussion while I take a look at the last two questions in the chat box. So yeah, if you have any questions you'd like to ask yourself, please go ahead and let us know.
Yeah, so I can respond to the question from Michiko.
Sure.
Yes, the 8% drop in total trips and the 4% increase in pooled opt-in, does this mean that people are less likely to take TNC trips and maybe driving themselves? Yeah, that's a great question. In this study, we do not know what those travelers are doing instead of taking those trips. It does mean people are less likely to take trips in those zones at those times. So it's possible that they're moving to travel at different times outside the zone. But what's more likely is that they're switching to other modes. We do have a study in the works to look at the transit data and see if we can detect changes in bus ridership and the ridership on the L that coincide with these changes in the fees. So we can see what kind of effect there was on mode shifting. For private vehicles, I would love to see that, but I don't know how to get data on how much private vehicle travel there was in these corridors at these times. So I don't think I'd be able to figure that out. I guess the only thing we can infer is for those riders who don't go to transit, either they're forgoing travel or they're taking some other mode, so we might kind of assume that they're taking private vehicles. Yeah, and that's a good point, Matt. There might be more micromobility trips as well. So we do have some data on bike and scooter sharing from Chicago, and we've also considered looking at that to see if the policies have an effect on use of those. So that's possibly something we could do as well. Of course, those short trips are also things where people could walk. And so perhaps there's like a filtering we can do and figure out if there's a subset of trips that are really short, maybe we consider walking as a potential alternative. But there's a lot of these trips are probably not going to be walked as an alternative, just it'll be a much longer trip.
Great, thank you, Jeremy. And there's also a question from Deborah. It makes sense that this tax scheme would have the desired effect. Do you have any comments about the magnitude of the effect? Did you investigate any measures, perhaps elasticities, that could give us insight into that magnitude?
Yeah, so what we don't know is how much of the tax was truly a pass-through to the customer. So what we know is that after January 2020, the TNC was charged for a tax for this trip. And if you look at the ride receipts that people use taking Uber and Lyft, if they want to, they can drill down and see that tax is part of the fee for their ride. But most people don't do that. They just see the overall top number. And of course, Uber and Lyft are doing this dynamic pricing, strategic pricing. They're trying to balance supply and demand. We don't know how much Uber and Lyft might be eating the cost, passing it on to the customer, or even inflating the cost as it gets passed on to the customer. We don't see that. We do see transaction prices. And so we have talked about whether we could identify the pass-through as like another type of study. There's some methodological challenges with that. So that makes it hard to get just like pure elasticity because we don't know what part of the price the customer sees. But what we could do, this 8% drop in total trips, we could certainly compare that to the increase in the tax and like look at that ratio. I'm just not sure it's not quite the same as a price elasticity.
Makes sense. Thank you. So Matt, I actually had a question for you, Matt Bruchon. Were there any other costs that you would have liked to have included in your analysis that you weren't able to? I think you spoke a little bit to this in one of your responses, but if you can sort of give us some more insight there.
Yeah, so the first one that comes to mind, definitely, the comment from Machiko in the chat about COVID risks. It's an important question how much people value having that solo ride in an era of a pandemic. I haven't scanned the literature to see if there have been any studies on that, but if anybody knows of any, I'd be curious to see. So that certainly would be one. Another one would be not necessarily a new cost, but just looking more at the heterogeneity of the costs. So for one thing, our study was limited to Chicago. So we only really thought about things like fuel costs as they pertain to that city specifically. You could get a very different result in a city with lower gas prices, for example. And another thing would just be you might have this very heterogeneous travel time valuation. So depending on things like whether it's the morning commute or somebody going home from the bar at night, the willingness to wait as well as the willingness to share the ride could be very different. And that's another thing that I'm interested in examining more.
Great, thank you. So at this time, does anyone have any further questions for any of our prior speakers? Thank you to all of our presenters. Really interesting work and really great presentations. If we don't have any further questions, we can go ahead and end the session. We do have 4 other sessions in BTR that start right after this one. So if the technical team could maybe share that agenda, we have a transportation safety session, an electrified transportation session, and 2 flash sessions with some shorter talks. So hope that you all will consider checking those out. And yeah, thank you again to the presenters. Really great session.
Thank you, Atiyya.